Hey team, in this video we're going to be looking at how to split a fraction up into partial fractions. Now there's a few ways to do this, but for this video we're going to use the most efficient way, I think, for these types of partial fractions. And let's just get into it. So worked example 2.4, write 4x plus 5 over x minus 1, x plus 2 in partial fractions. Okay. So our denominator is a product, all right? So what we can do is we can split this fraction up. Now, what into two fractions, one with a denominator of x take 1, one with a denominator of x take 2. Now, we don't know what the numerators are going to be. All right, so we just give them constants for now, all right, a and b. Now, if we compare the two forms, so let's imagine that using what we've written here, we've put the fraction back together, or we've rewritten the fraction as a single fraction again, then we would get something like this, right? So a outside of x plus 2 plus b outside of x plus 1. So if we were to rewrite this as a single fraction, that's what our numerator would be. And that will equal 4x plus 5. Now we don't need the denominator anymore because we're just trying to equate the numerators. All right, so now that we have this equation, we can try to solve for a and b. Okay, now there's a few ways of doing this, but the way that's quickest would just be trying to eliminate either a or b. So let's say let x equals, so let's think about this term here. If we want to try to eliminate a completely, all right, what would x have to equal? It has to equal -2 because that would make the bracket 0. So let x equals 2, x equals -2, then our equation would now become b, all right, outside of -2 take 1, so -3, and then let's sub in -2 on the right hand side, so we get -8 plus 5, so -3b equals -3, so therefore b equals 1. All right, we found b really quickly. And now let's try to solve for a. So if we want to solve for a, we need to eliminate b. So ask ourselves, what does x have to equal if we want to get rid of b? Well, it has to equal 1. So when x equals 1, the equation looks like this. So a times 3 equals 9. Therefore, a equals 3. So if we want to substitute in our newly found values, our partial fraction is 3 over, x take 1 plus 1 over x plus 2. Okay, so these are the numerators you need to arrive back at the original fraction if you were to add these two fractions. All right, so using that technique, let's keep going. Worked example 2.5. Okay, so now part A, all right, let's just do that again, but then part B and C, we kind of have to apply what we've already learned from last term. So A, all right, so express 1 over x plus 1 2x plus 1 in the form a over x plus 1 plus b over 2x plus 1. So let's get an expression for, let's equate the numerators. So if we start with a outside of 2x plus 1 plus b outside of x plus 1, all right, that should equal 1. Now let's find a and b. So let x equals, let's find a first. So if we want to eliminate b, we'd have to let x equals -1. That means a outside of, alright, 2 times -1 plus 1 is -1 equals 1, so therefore a equals -1. And then if we try to solve for b, we need to eliminate a. So if we want to eliminate a, x has to equal -12. Alright, because 2 times -12 plus 1 would equal 0. So that means b equals, b multiplied by -12 plus 1 is half equals 1. So therefore b equals 2. So the partial fraction would be, well, solution to part A would be 1 over x plus 1 times 2x plus 1 would be equal to -1 over x plus 1 plus 2 over 2x plus 1. Alright, so there's our partial fraction from A. Now let's do B. Hence, find the first three terms of in the expansion of our fraction. Alright, so this is where we have to use the rule to expand a, this is the binomial expansion with rational powers, right, from exercise 2 AHL. The reason that we got partial fractions first was to kind of, so that we can expand, have an expression for each term, and then we can add them together, rather than trying to expand this, because we haven't really, well, that would be a quadratic, and we haven't looked at how to do that. We don't know how to do that. Alright, so let's take our partial fraction, and we want the first three terms. So that means we want to expand up to x squared, because you'll see in a second if you've forgotten. Alright, so first thing, we want to rewrite this. I don't need the 1 there. Alright, so use my index laws. Okay, now we have a rational power, and now we can apply the formula for the infinite series to expand each bracket. So this is where you need to kind of, I don't think this is in the formula booklet, so make sure you remember this one. So the formula is 1 plus n x plus, now we only want up to the x squared term, so I'll stop at the next term, n, which is your power, n minus 1 over 2 factorial, which is 2, multiplied by x squared, and then make sure you write plus ... because this is an infinite series. And then we need to do the same with the second term. Alright, a bit of work here, a bit of working, a lot of working. Alright, so 1 plus n x. Now remember, your x is basically your whole term there. That might be a little bit confusing, but just make sure you understand the distinction when you go over this again. Plus n minus 1. I should just write -2, but that's fine. Over 2 factorial, which is 2, and then x squared, need more space, plus ... Alright, now we actually need to expand, or simplify, sorry. So what's that? plus x squared plus dot 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 plus 2 outside of morning. 1 take 2x, negative 1 times negative 2, well, that's plus 4x squared plus dot 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 equals negative 1 minus x squared plus dot 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 plus 2 minus 4x plus 8x squared plus dot dot dot. Okay, and then we just collect all these like terms. And these are all the terms we want because we want the first 3 terms, so that includes the constant term, the x term, and the x squared term. So 1 take 3x plus 7x squared, and then just write plus dot 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 because we don't need the rest, and there we have it, that's B. Okay, and finally, state the range of values for which this expansion converges. Alright, so since we have 2 expansions, alright, this one, so the first expansion will converge when, remember the conditions for convergence, absolute value of x is less than 1. Alright, now our second term, 2 outside of 2x plus 1 take 1 will converge when absolute value of 2x is less than 1. So that means that the absolute value of x would be less than half. Now we need to select the condition that can apply to both of these expansions, and that would have to be this one. Alright, x is less than half. Alright, because x is less than 1 does not apply to all of x is less than half, or mod x. Alright, so I've highlighted our solution there.